The hairy ball theorem, a ball covered in hair, like a fuzzy tennis ball. The theorem says you can't smoothly comb down all the hair on this ball without creating a tuft, like a cowlick on your head, somewhere. In mathematical terms, it's about continuous tangent vector fields on spheres. A tangent vector field assigns a direction, a vector, to each point on a surface, like the sphere. Think of it as combing the hair at each point on the sphere in a consistent direction. When combing the hair on a fuzzy ball, like a coconut or a tennis ball, no matter how you comb, there will always be a spot where the hair stands up, just like a cowlick. Henri Poincaré first proved this for the two-sphere, the ordinary sphere, in 1885. Later, Luitzen Egbertus John Brouwer extended it to higher even dimensions. Next time you see a hairy ball, remember that even math has rules for combing. The Dichotomy Paradox. Zeno's paradoxes are a set of philosophical problems that question how motion is possible. The Dichotomy Paradox is one of them. In the paradox of the cheetah and the snail, a cheetah is in a race with an espresso-charged snail. Suppose that the cheetah is sprinting at 10 meters per second, that the snail is zooming at 1 meter per second thanks to the espresso shot, and that the snail starts 9 meters ahead of the cheetah. On the face of it, the cheetah should catch the snail after 1 second, at a distance of 10 meters from where it starts, and 1 meter from where the snail starts. Before the cheetah can catch the snail, it must reach the point where the snail started. But in the time it takes to do this, the snail slithers a little further forward. So next, the cheetah must reach this new point. But in the time it takes the cheetah to achieve this, the snail inches forward a tiny bit further. And so on to infinity. Every time that the cheetah reaches the place where the snail was, the snail has had enough time to get a little bit further, and so the cheetah has another run to make. Zeno concludes that the cheetah has an infinite number of catch-ups to do before it can catch the snail, and so the cheetah never catches the snail. The birthday problem. The birthday problem in probability theory asks, what is the chance that, in a group of n randomly chosen people, at least 2 of them share the same birthday? The birthday paradox refers to the surprising fact that you only need 23 people for there to be a better than 50% chance that 2 of them share a birthday. This is a veridical paradox, meaning it seems wrong at first, but is actually true. At first, it seems unlikely that 23 people would be enough for a 50% chance of shared birthdays, but it makes more sense when you consider the number of birthday comparisons. With 23 people, there are 23 times 22 divided by 2 is equal to 253 pairs of people to compare, which is much more than half the number of days in a year, 365. This concept has real-world uses, such as in cryptography. A birthday attack uses the birthday paradox principle to find 2 different inputs that produce the same hash value more efficiently, exploiting the likelihood of collisions in hash functions. The problem is often credited to mathematician Harold Davenport around 1927, though he didn't publish it because he assumed someone else must have discovered it earlier. The first published version was by Richard von Mises in 1939. The National Security Agency, NSA, has used the principles behind the birthday paradox to understand and design secure hash functions. In the 1980s and 1990s, cryptographers realized that the birthday paradox could be used to mount efficient birthday attacks on hash functions. A hash function takes an input and produces a fixed size string of characters, which appears random. For a secure hash function, it should be computationally infeasible to find 2 different inputs that produce the same hash output, a collision. However, due to the birthday paradox, if you have a large number of different inputs, the chances of finding a collision increase dramatically. This understanding led to the development of more robust cryptographic standards and practices, ensuring that hash functions are secure against such probabilistic attacks. The elevator paradox. The elevator paradox is an interesting phenomenon observed by 2 physicists, Marvin Stern and George Gamow, who worked in a tall building. Gamow noticed that the first elevator to stop at his floor near the bottom was usually going down. Meanwhile, Stern, who worked near the top floor, observed that the first elevator to stop at his floor was usually going up. This seems to suggest that elevators are more likely to be going in one direction depending on which floor you're on, which is a bit confusing at first. Imagine a building with 30 floors and 1 slow elevator. The elevator stops at every floor as it goes up and down. If you're on the first floor and walk up to the elevator at a random time, most of the time, the elevator will be on its way down. This is because the elevator spends a lot of time traveling down through all the floors after reaching the top. If you're on the 29th floor, the elevator will usually be coming up to pick up people going to the top floor, so it will be more often going up when it first stops at your floor. The elevator takes 1 minute to travel between each floor. If you stand by the elevator doors on the first floor and just wait, it takes the elevator 30 minutes to go up to the top floor and 30 minutes to come back down to the bottom. That's 60 minutes for a full round trip. During this time, the elevator is only going up past the first floor for the first 2 minutes of each hour, from 0 to 2 minutes. The rest of the time, 58 minutes, it's coming down past the first floor. So, if you walk up to the elevator at a random time, there's only a small chance, 2 out of 60, it's going up, and a big chance, 58 out of 60, it's going down. The same idea applies if you're near the top floor, but in reverse. The elevator is more likely to be on its way up to the top floor when it first stops at your floor. The elevator paradox is about how elevators seem to be more likely to be going in one direction depending on which floor you're on. This makes it seem seem like it's always going in the opposite direction of where you want to go. Banach-Tarski Paradox. The Banach-Tarski Paradox is a mind-bending concept in geometry. It basically says you can take a solid ball, chop it into a few pieces, then rearrange them into two identical solid balls without stretching, bending, or adding anything. Sounds crazy, right? What's even weirder is that these pieces aren't normal solids. They're made up of infinitely many points scattered around. So when you put them back together, you're not dealing with traditional volumes. This idea challenges our basic geometric intuition. Normally, when you move things around without changing their shape, you expect the volume to stay the same. But here, that's not the case. Even though the pieces themselves don't have volumes you can measure, putting them together creates something with a volume. The proof of this paradox relies heavily on certain principles in set theory, especially the axiom of choice, which lets you make some funky sets that don't behave like normal ones. Surprisingly, it's been shown that you can move these pieces around smoothly without them crashing into each other. Now, if we switch gears a bit and look at this paradox through a different mathematical lens called locales instead of traditional spaces, it doesn't break the rules anymore. In this abstract setup, you can have spaces without points, but they're still not empty. And when you consider these intersections of pieces, they have a kind of hidden mass that can be measured, making everything fit together nicely in the end. It's a mind-bending result that shows how counterintuitive infinity and set theory can be.
Simpson's paradox. Simpson's paradox is often presented as a compelling demonstration of why we need statistics education in our schools. It was first noted by Edward H. Simpson in 1951, who observed that the overall combined data can sometimes mask important insights that became evident when looking at subgroups. This paradox occurs when trends observed in different groups of data reverse upon combining those groups. Assume that there is a new treatment for a disease. You look at two groups, both males and females. Among males, 70% of treated patients survive, while only 30% of untreated patients survive. Among females, 80% of treated patients survive, while only 40% of untreated patients survive. Based on these separate groups, it seems like the treatment is very effective for both males and females. Now let's combine the data. In the combined group of males and females, 50% of treated patients survive, while 60% of untreated patients survive. Surprisingly, when you look at the combined data, it appears that the treatment is less effective or even harmful. This reversal of the trend when the groups are combined is known as Simpson's paradox. The paradox happens because of a third variable, called a confounder, which affects the two groups differently. In this case, the third variable could be something like the severity of the disease, which might vary between males and females, affecting the overall survival rates. To decide whether the treatment is truly effective, you need to look at the data carefully, considering the impact of the third variable. In some cases, the combined data gives a right conclusion, and in others, the separate groups give the correct answer. The Monty Hall Problem. You're on a game show and there are 3 doors. Behind one door is your dream car, and behind the other 2 are goats. You pick a door, let's say door A, then the host, Monty Hall, who knows exactly what's behind each door, opens another door, say door B, revealing a goat. Now he gives you a choice, stick with your original choice, door A, or switch to the remaining unopened door, door C. Intuitively, it might seem like it doesn't matter if you switch or not, because there are 2 doors left, so the chances should be 50-50. But surprisingly, if you switch doors, you actually have a higher chance of 2/3 winning the car compared to your initial choice of 1/3. The key insight is that Monty's action of revealing a goat provides new information that changes the underlying probabilities. Initially, each door has a 1/3 chance of hiding the car. After Monty opens a door with a goat, the door you initially pick still has a 1/3 chance, but the combined probability for the other 2 doors, since Monty won't reveal the car, becomes 2/3. Therefore, switching to the other door increases your chances of winning to 2/3. Now, if there are 100 doors, behind one is a new game console, behind the other goats, you pick door 1. Monty opens 98 other doors, all goats. Now you have door 1 and door 73 left. Should you stick or switch? Switching to door 73 now gives you a 99% chance of winning, because Monty's actions shows where the goats are, making door 73 very likely to have the console. The Sleeping Beauty Problem. Sleeping Beauty agrees to participate in an experiment. On Sunday, she is given a sleeping pill and falls asleep. During the experiment, a coin is tossed secretly. If it lands on heads, she's woken up on Monday, given another sleeping pill, and then woken up again on Wednesday. If it lands on tails, she's woken up on both Monday and Tuesday, each time given a sleeping pill, and then woken up again on Wednesday. Importantly, each time she wakes up, she doesn't know if it is Monday or Tuesday, and she doesn't know the outcome of the coin toss. Put yourself in the position of Sleeping Beauty. You wake up, you don't know what day it is, and you don't know if you have been woken up before. You only know the theoretical course of the experiment. Now the question is, what is the probability that the coin toss landed heads when she is asked about it after each waking? One camp argues it should be 1/2, 50%, because at the start of the experiment, whether it's heads or tails is equally likely, regardless of the day she wakes up. The other camp argues it should be 1/3, about 33.3%, because there are 3 scenarios: heads on Monday, tails on Monday, and tails on Tuesday. Since tail scenarios happen twice as often as head scenarios, once for Monday and once for Tuesday, the probability should be 1/3. Imagine repeating the experiment many times. In the long run, Sleeping Beauty would wake up after heads roughly 1/3 of the time, and after tails on Monday or Tuesday, each roughly 1/3 of the time, and 2/3 total for tails. This long run experiment should apply to the single trial as well, suggesting 1/3 for heads. The Sleeping Beauty problem is a famous thought experiment with no universally agreed upon answer. The ant on a stretching rope problem. Imagine an ant standing at one end of a rubber rope that's initially 1 kilometer long. The ant crawls at a steady pace of 1 centimeter per second. However, every second the rope stretches uniformly. After the first second, it's 2 kilometers long. After the second second, it is 3 kilometers long, and so on. The question is whether the ant will ever reach the far end of this rope. Surprisingly, the answer is yes. And here's why. Initially, the ant moves forward 1 centimeter, which is 1/100,000th of the original 1 kilometer length. After the first second, when the rope stretches to 2 kilometers, the ant moves another centimeter, and now the centimeter is 1/200,000th of the new 2 kilometer length. If you sum up all these fractions over time, it forms a series. This series is known as the harmonic series, and it actually diverges into infinity. This means that no matter how large the rope stretches each second, the sums of these fractions will eventually exceed 1, ensuring that the ant will reach the end of the rope. Berry Paradox. Berry's paradox is how we define numbers with very specific rules. Imagine trying to define a number using a description that states it cannot be described in fewer than 23 syllables. The catch is that the phrase itself has only 20 syllables. This creates a contradiction because a number it defines supposedly requires more syllables to describe than the phrase itself. Berry's paradox extends beyond mere wordplay. It has implications in fields like algorithmic information theory. Specifically, it suggests limits on the ability to compute the Kolmogorov complexity of a string in general. Kolmogorov complexity measures the shortest computer program or description that can produce a given string. But Berry's paradox hints at cases where such descriptions might become self-contradictory or impossible to construct. Thus, it highlights deeper issues in defining and computing complex entities based on their descriptions or definitions. Absent-minded driver. An absent-minded driver who starts at a point called start on a map. From there, they encounter an intersection called X. At X, the driver can either exit and end up at location A with a payoff of 0, or they can continue to another intersection called Y. At Y, the driver faces another decision. Exit to get to location B with a payoff of 4, or continue to another location C with a payoff of 1. The twist is that the driver cannot tell the difference between intersections X and Y, and can't remember if they've already passed one of them before. This lack of distinction makes the decision-making process quite complex. At the starting point, start, the problem seems straightforward. If the driver chooses to continue with a probability P at each intersection, the expected payoff can be calculated. It turns out that the optimal strategy P here is 2/3. However, the paradox arises when considering what happens when the driver reaches an intersection, say X or Y. At that moment, the driver should consider the probability A that they are at X, and thus 1 minus A that they are at Y. The optimal decision, P, to continue then changes compared to the optimal decision at start. This inconsistency challenges the initial optimal strategy found at start. Hooper's Paradox. Hooper's Paradox is a fascinating puzzle that plays a trick on our perception of area. Imagine you have a geometric shape with a total of 32 square units. This could be any shape, but for simplicity, let's say it's a combination of triangles and other shapes that together make up this area. You carefully cut this shape into 4 smaller pieces. These pieces are specifically designed to fit together in a new way. Now you take these 4 pieces and rearrange them to form a rectangle. When you look at this new rectangle, it seems to cover only 30 square units instead of the original 32. It looks like 2 square units have disappeared. Here's a trick to understanding the illusion. To understand where those 2 squares went, we need to look closer at the pieces. Original triangles. And the original shape, there are right-angled triangles. One of the sides of these triangles, the shorter side at the right angle, is exactly 2 units long. Reassembled triangles. When you inspect the triangles in the new rectangle, you notice that the same side is now only 1.8 units long. The slight difference in the side lengths mean that the pieces don't fit perfectly together in the new rectangle. Instead, they overlap a little bit when arranged into the rectangle shape. The overlapping area is a small parallelogram, a shape similar to a slanted rectangle. To find out exactly how much area is overlapping, you can use mathematical formulas. Specifically, you can use the Pythagorean theorem and the Heron's formula. The Pythagorean theorem is to find the lengths of the sides and diagonals of the overlapping parallelogram. And for the Heron's formula, it is to calculate the area of the parallelogram, and Heron's formula allows you to find the area of a triangle when you know the lengths of its sides. When you do the math, you find that the area of this overlapping parallelogram is exactly 2 square units. This explains the missing area. The original shape, 32 square units, the new rectangle without overlapping, 30 square units, and the overlapping area has 2 square units. So the 2 square units haven't disappeared, they are just hidden in the overlap. This clever arrangement creates an optical illusion that makes it seem like the area has vanished. Bertrand's paradox. The Bertrand paradox is a problem in probability theory that shows how the way we define randomness can affect the outcome. Joseph Bertrand introduced this problem in 1889 to highlight that probabilities might not be clear if the method of choosing a random variable isn't well defined. Imagine you have a circle with an equilateral triangle in it. Now, if you randomly pick a chord, a line connecting the 2 points of a circle, what is the chance that the chord is longer than the side of the triangle? Bertrand came up with 3 ways to randomly pick a chord in a circle, and each way has a different chance of getting a chord that's longer than a side of an equilateral triangle inside the circle. First, in the random endpoints method, you pick 2 random points on the circle and draw a line between them to make a chord. If you rotate the triangle so that one of its corners touches one endpoint of the chord will be longer than a side of the triangle if the other endpoint falls within a certain 1/3 arc of the circle. The chance of this happening is about 1/3 or 33%. Second, in the random radius method, you start by choosing a random line from the center of the circle out to its edge. This line is called a radius. Then you pick a random point along this line and draw a chord that's perpendicular to the radius and goes through that point. The chord will be longer than a side of the triangle if the point you pick is closer to the center of the circle than where the triangle's side touches the radius. The probability of this happening is 1/2, or of course 50%. Lastly, in the random midpoint method, you choose a random spot inside the circle and use that spot as a middle point of the chord. The chord will be longer than a side of the triangle if the point you picked is within a smaller circle that's half the size of the original circle. The chance of this happening is 1/4 or 25%. These different methods of picking chords each give a different answer to the same question. This shows that the definition of randomness affects the probability result, highlighting the importance of clearly defining how randomness is generated in probability problems. Hilberts Hotel. Hilberts Hotel is a thought experiment proposed by German mathematician David Hilbert in 1925. It involves a hotel with an infinite sequence of rooms, 1, 2, 3, and so on to infinity. This is called countable infinity, since each room can be associated with a counting number. The hotel starts out fully occupied. However, a new person shows up and wants a room. Surprisingly, you can accommodate the new guest without removing any current guests. The hotel simply moves the guest in room 1 to room 2, the one in room 2 to room 3, etc. In general, the guest in room n moves to room n+1. Afterward, room 1 is free for the new guest. Hilberts Hotel can also accept a countably infinite number of new guests. The guest in room 1 moves to room 2, the one in room 2 to room 4, and in general, the guest in room n to room 2 times n. This leaves the odd-numbered rooms free for the new guests. The fact that Hilberts Hotel can accommodate new guests despite being full is known as Hilberts Paradox. This is an example of a veridical paradox, a statement that is true despite seeming false. Cantor's diagonal argument. Cantor's diagonal argument is a proof that the cardinality of the set of real numbers is greater than the cardinality of the set of natural numbers. The cardinality of a set can be thought of as its size. This proof was published by Georg Cantor in 1891. To prove this fact, it is sufficient to show that there are more real numbers between 0 and 1 than there are natural numbers. If this is the case, then there are definitely more real numbers than natural numbers. The proof is by contradiction. A proof by contradiction starts with an assumption and shows that the assumption leads to an impossible conclusion, thus proving that the assumption is wrong. In Cantor's diagonal argument, we begin by assuming that the set of real numbers between 0 and 1 and the set of natural numbers have the same cardinality. If so, that means each real number can be paired with a natural number 1 to 1 with no numbers left over, so let's do that and put the pairs in a list. Our list of pairs will have the natural numbers on the left and the real numbers on the right, making sure the digits of the real numbers are aligned with each other. Then, we draw a downright diagonal through the digits of the real numbers. Now let's construct a new real number. Starting at the top left of the diagonal, take the first digit of the first real number and change it to something else. For example, if it is 9, subtract 1 from it, otherwise add 1. We will put this digit in our new number. Now, go down the diagonal, repeating this process for all the real numbers in the list. So is our new number a part of the list? Well, it can't be the first number in the list since the first digits don't match. It can't be the second number either since the second digits don't match. Our new number will always differ from any given number on the list since there will always be at least one digit that does not match the digit on the diagonal. Thus, we have a real number that isn't part of the list, meaning we haven't achieved a one-to-one pairing, which contradicts our earlier assumption. Even if we insert this new number into the list, we can just repeat this process to generate more and more new real numbers. This implies that there are more real numbers than there are natural numbers. The idea that some infinites are bigger than others is counterintuitive, but it is a true fact. Thomson's lamp. Thomson's lamp is a hypothetical device proposed by British philosopher James F. Thomson in 1954. It is a lamp that can be switched on and off as fast as you want. Let's say that you start a timer and turn the lamp on. You wait 1 minute and then you turn the lamp off again. After another half a minute has passed, you turn the lamp back on. Each time you wait for half of the previous amount of time and then you toggle the lamp. Because the lengths of these intervals add up to 2 minutes, you will have toggled the lamp an infinite amount of times after 2 minutes have passed. A task like this with an infinite amount of actions in a finite amount of time is called a supertask. But when you are finished, will the lamp be on or off? Each time you toggled the lamp off, it was immediately followed by toggling it back on and vice versa. Thus, it seems like the question has no logical answer, which creates a paradox. Mathematically, this is related to the behavior of a certain infinite sum. 1 minus 1 plus 1 minus 1 and on forever, and that's kind of a tongue twister. An infinite sum like this is called a series, and this particular one is called Grandi's series, named after Italian mathematician Guido Grandi. Because the result just bounces back and forth between 0 and 1 forever as you take more and more terms, the series doesn't approach a specific number or converge. So we say that it diverges or has no finite value. However, certain methods can be used to assign these series a meaningful value. For instance, you can take the averages of the results as you go along, known as Cesaro summation, which gives a value of 1/2. Thomson had heard of Grandi's series being given this value, but his thought experiment did not allow the possibility of the lamp being half on. Thus, he rejected that Grandi's series and his thought experiment had any direct relation. Gabriel's horn. Gabriel's horn is an infinitely long, horn-shaped object with a finite volume but an infinite surface area. It was first considered by Italian mathematician Evangelista Torricelli in a paper published in 1643. In order to form Gabriel's horn, take the graph of the curve y equals 1 over x in the xy plane, with the domain of x being greater than or equal to 1. Then rotate this curve in 3 dimensions around the x-axis and fill in all the points that the curve passes through, forming a surface. A 3-dimensional surface created by rotating a curve around an axis like this is known as a surface of revolution. Now imagine closing off Gabriel's horn with a cap. We can find the volume of the inside region using integration. Using slices perpendicular to the x-axis, slice the inside region into thin disks that are approximately thin cylinders. Labeling the radius of each cylinder as r, the base area of each of these cylinders is pi r squared, and the little thickness is dx, so the volume is approximately pi r squared times dx. The radius at each point is just the distance between the x-axis and the graph of the function 1 over x, so we can replace r with 1 over x. So the volume of each cylinder is approximately pi times 1 over x squared times dx. And we just have to integrate this from 1 to infinity, which gives us pi. So the volume of this region is pi. But what if we just find the area under the curve y equals 1 over x, or x from 1 to infinity? This is the same as this, which becomes this. As b grows bigger and bigger, the natural logarithm of b also grows bigger and bigger without bound, so the area under the curve is actually infinite. This is despite the fact that when we rotate this around the x-axis, the volume of the solid we get has a finite value of pi. Due to the counterintuitiveness of this fact, mathematicians at the time of its discovery perceived it as a paradox. Ross-Littlewood Paradox. The Ross-Littlewood Paradox, invented by John E. Littlewood in 1953 and further explored by Sheldon Ross in 1988, involves an infinitely large empty vase and an infinite amount of balls. A supertask is performed. At each step, 10 balls are put in the vase, and then 1 ball is taken out. Each step takes half the amount of time as the previous one to ensure that the task is completed in a finite amount of time. Now at the end, how many balls does the vase contain? The intuitive answer appears to be infinitely many. Each step seems to involve a net increase of 9 balls in the vase, so the number of balls just grows towards infinity. However, there is a sense in which the vase may be empty. Imagine that, at the start, all of the balls are numbered. At step 1, you put in balls 1 through 10 and remove ball 1. At step 2, you put in balls 11 through 20 and remove ball 2, and so on. For each step number n, the ball numbered n is removed from the vase. Eventually, ball number 1000 will be removed, then the ball number 1,000,000, and so on. Since there are no balls that don't eventually get removed, by the end, all of the balls must have come out. There is no general agreement on the solution to this paradox. Besides the previous solutions, some people think it depends on exactly which balls you take out of the vase. Others think that the problem does not give us enough information to state the answer, or that it isn't well defined. Dartboard Paradox. The Dartboard Paradox is a paradox in probability. Let's say you have a dartboard and you randomly pick some point on it. Now let's say a dart hits the dartboard at a random point. Is it possible for the dart to exactly hit the point you picked? And if so, what is the probability that this occurs? This is a mathematical scenario, so we will assume that the point is infinitely small. The answer to the first question is obviously yes. The dart can hit any point on the dartboard after all. However, since your point is only one point out of infinitely many, it seems that the probability of hitting that point is actually 0. Indeed, in a rigorous mathematical sense, this is actually the case. But you can also use the same logic for any other point on the dartboard. So the probability of the dart hitting any given point on the dartboard is 0 as well. However, this seems counterintuitive, since we said that a dart must hit the dartboard. The problem is that probability 0 does not mean impossible. In this case, what we have is known as a continuous random variable because the space of possible contact points for the dart is continuous. This is as opposed to a discrete random variable where there are only a finite number of possible outcomes, such as the roll of a dice. Continuous random variables are common in probability. For example, the normal distribution models a continuous random variable. In this case, it is often more useful to talk about the probability that a given event falls within a specific region of the possibilities. For example, you can ask about the probability that the dart will land on the dartboard's upper right quadrant. In this case, the probability is 1 in 4 or 25%. When using a continuous distribution, such as the normal distribution, the probability of an event happening in a certain region is equal to the area between the graph of the distribution and the horizontal axis within that region, which can be calculated using integration. Petersburg Paradox. The St. Petersburg Paradox is another probability-based paradox named for the city St. Petersburg, where Daniel Bernoulli studied it. Imagine a casino game beginning with a stake of $2. The stake is the amount the player will be paid at the end. The player flips a coin, and if it lands on tails, the stake doubles. Otherwise, the game ends, and the player gets the stake. We can calculate the expected value of the player's earnings. The expected value is the average value that you would predict from a random process. There is a 1/2 chance that the player lands on heads immediately, earning $2. Given the 1/2 chance of landing on tails to start with, there is then a 1/2 chance of landing on heads on the next flip and earning $4, giving an overall chance of 1/4 to earn $4. This logic continues for all remaining flips. We can calculate the expected value by multiplying each payout by its probability and adding the results together. 1/2 times 2 plus 1/4 times 4 plus 1/8 times 8 is the same as 1 plus 1 plus 1, and this is the same as infinity since it will keep going on. Now, what would be a fair cost to play this game? Hypothetically, no matter the cost, even if it was $1 billion, the casino always loses. However, according to Ian Hacking, few people would pay even $25 to play this game, which isn't a paradox. Riemann series theorem. The Riemann series theorem, named for and rigorously proved by German mathematician Bernhard Riemann, involves conditionally convergent series. A conditionally convergent series is an infinite sum that converges to a particular finite value, but would not converge if you added up the absolute values of the terms instead. In other words, a conditionally convergent series converges only under the condition that the sign of each term is taken into account. This is as opposed to an absolutely convergent series, which converges in both cases. According to the Riemann series theorem, any given conditionally convergent series can be rearranged to produce any real number. This runs counter to how finite sums work. In a finite sum, rearrangement of the terms doesn't affect the result. To prove the Riemann series theorem, consider grouping all the terms of a conditionally convergent series into two groups, a positive and negative in descending order of magnitude. Since the series is convergent, the magnitudes of the terms in each group must get arbitrarily small. However, remember that the series is only conditionally convergent. That means that each group of terms individually doesn't sum to a finite value. If the positive terms were to sum to some positive value a, and the negative terms were to sum to some negative value minus b, then the overall sum of the absolute values of the terms would be a plus b, implying that the series would be absolutely convergent, not conditionally convergent. It's also impossible that the positive terms sum to positive infinity, while the negative terms sum to a finite negative value. Otherwise, the original series would diverge towards positive infinity, not converge. This is also true the other way around. Thus, the only possibility is that the positive terms sum to positive infinity and the negative terms sum to negative infinity. Due to the fact that these are unbounded, we can combine terms to go as high or low as we want. In order to test this out, let's pick any real number x and try to get to it by adding our terms. We start at 0. If x is above us, we add the largest positive term we haven't used. If x is below us, we add the negative term of greatest magnitude that we haven't used. If we are currently at x, we can add either a positive or a negative term. We can repeat this process indefinitely, going as far up or down as we need, and gradually converging on x as our terms get smaller and smaller. Also, another paradox is that if you hit that subscribe button, it magically turns gray. Anyways, I'll catch you guys in the next video.